axis of the rotation is axis of the rod. The third case is case 3. Case 3 will become the axis of rotation. The axis of rotation is the axis of rod. It means let it see the rod, and where is axis of the rod, and this axis of the rod is the axis of rotation itself, and this rod is rotating in this manner. Now see, as we previously told, the moment of inertia depends on the mass distribution. Now see, as the thickness of the rod is negligible, so what is its upper limit of integration? That will be the lower limit of the integration. So its moment of inertia I becomes what? Integration of r square dm. Okay. Now see, but its upper limit is what? 0, and lower limit is 0, because these two axes coincide with each other. There is no distance, no difference. So this becomes integration of r square m divided by l into dr, and limit 0 to 0. So it will become m divided by l into integration of r square dr. This is the limit. So from any integral, if the upper limit and lower limit both are same, then its integral value will be 0. So in any integral, if the upper limit and the lower limit of the integral are same, it implies integral becomes 0. So in that case, moment of inertia, it implies moment of inertia I, moment of inertia I becomes what? 0 for this situation. Now we'll take another situation for a rod. So what will happen if there is case 3. So what will be the moment of inertia when the position of the axis of rotation is different from the above cases? Now see, this is the position of the rod, and the length of the rod is L, and this distance is D. So one end of the rod is at a distance D from the axis of rotation, and other end is at a distance L plus D. So what will be the moment of inertia for this rod? Now from the basic principle, we will write the formula for moment of inertia. So what is formula of moment of inertia? Formula of moment of inertia is I equal to what? I equal to integration r square dm. And what are the limits? Lower limit is d, because the left end of the rod is at a distance d from the axis of rotation, and upper limit becomes the right end of the rod. It becomes L plus D. So it becomes what? It becomes R square. What is dm? Dm is nothing but, what is dm? Let this element is dr, and distance from the axis to this dr element is r, and mass of this element is dm. So dm becomes what? Dm is equal to m divided by l into dr. Now we have to integrate this from the limit d to d plus l. So our moment of inertia becomes what? Our moment of inertia becomes m divided by l into integration of r square dr, and its lower limit is d, upper limit is d plus l. Now as we know, integration of r square dr is r cube by 3. So I becomes I equal to m divided by l into integration of r cube divided by 3, and its corresponding limits are d to d plus l. It will become m divided by 3l. Why 3l? Because 3 is constant, and its limit is d plus l, first upper limit minus lower limit, minus d cube. So I becomes what? I becomes m divided by 3l, and it becomes, if we calculate this, d plus l cube equal to d cube plus l cube plus 3 d square l plus 3 d l square minus d cube. So this d cube and this d cube get cancelled. So after this cancellation, what we get? So moment of inertia of this rod I becomes what? I becomes m divided by 3l into, and we see there is l cube, there is 3d square l, there is 3dl square. So we can take l as common. After taking common, the remaining thing is l square plus 3d square plus 3dl, and this get cancelled. So after cancellation, our moment of inertia becomes I equal to m divided by, becomes 1/3 m into l square plus 3d square plus 3dl. So this is the moment of inertia for this type of orientation of rods. Okay. Now we'll see for another configuration of the rod. So if the rod is at a distance, at another distance. Now we discuss about case 4. Now it will be about case 5. So case 5.